we'll now consider free vibration with damping. Okay, so just to set up the problem, we have a mass sitting in a plane connected to a spring with stiffness K and connected to a damper which produces a force, essentially a drag force, that opposes the velocity of the mass in some sense. Okay, so that's the situation here. And the position of the mass is measured from the rest position of the spring. Okay, and given the system, the equation of motion is mx double dot plus kx plus cx dot equal to 0. More sort of conventionally written as mx double dot plus cx dot plus kx equal to 0. Just to recall, the free body diagram for this situation would be kx like this and cx dot like this. So if you go ma, which is the acceleration, equals sum of all forces, you have kx minus cx dot. Okay, so that's the derivation of this equation. Okay, so let's call this equation 1. Now, what is the solution to this equation? We want to know the solution to this equation when c not equal to 0. C equal to 0 would be called undamped oscillation, undamped system. C not equal to 0 would be damped, would be considered damped, right? What is x of t? Now, before we derive an expression for x of t, let us transform the equation into something simpler looking. Transform the equation 1 into a more standard form. Okay, so let's do that. And we do that by first noting, of course, that omega n, the natural frequency, natural angular frequency, is square root of k over m. And then we define something called the damping factor or the damping ratio zeta, which is drawn like this. Zeta is defined as c, the damping coefficient, divided by 2m omega n in the denominator. Okay, so recall, c is called the damping coefficient, sort of like the drag coefficient. It's a damping coefficient, and then this quantity is called the damping factor or the damping ratio, which is the ratio of c and this quantity. Sometimes c not or is defined to be 2m omega n, would be called critical damping. So we'll come to that later. Okay, so what that means, critical damping. In any case, okay, so we're going to use this equation. We're going to transform this equation using this equation, equation number 2, and this equation, equation number 3. Okay, so how do we do that? We take equation number 1, mx double dot plus cx dot plus kx equal to 0, and then divide through by m. So divide by m. We get x double dot plus c over m x dot plus k over m x equal to 0. Right? And then we do the following thing. We, of course, we can multiply and divide this quantity by omega n. So let's do that. We actually multiply and divide by 2 omega n. X dot. And then k over m, we just substitute omega n square for that. Okay. And then we collect terms here. So we go x double dot plus c over 2m omega n times 2 omega n x dot plus omega n square x equal to 0. And of course, this quantity equals zeta, the damping ratio that we just defined. So we have x double dot plus 2 zeta omega n x dot plus omega n square x equal to 0. Okay. So equation 2 is essentially equation 1. Say this is the same equation, except we've replaced m, c, and k in terms of omega n and zeta. Okay, so equations 1 and 2 are equivalent, and we've just replaced m, c, and k in terms of zeta and omega n. Okay, so let's consider how we solve an equation like this. Solving equation 2 for x of t for some given initial conditions. How do we do that? Recall, this is a second order differential equation, linear second order differential equation, if you recall your differential equations class, and we can substitute a solution of the form x of t equals a e power lambda t. Okay, and then we plug that into 2. Let's call this equation 4. Use 4 in equation 2, and we get, so to plug in 4, we need to find x dot, which is lambda a e power lambda t, and then x double dot equals lambda square a e power lambda t. Let's call this actually 5 and 6. And we go use 4, 5, 6 in equation 2. Actually, I guess I should have called this equation 4 already. and this is equation 5. These are 6 and 7. Five, 6, 7 in equation 4, this guy. So we have, let's just write equation 4 again so that we can substitute things clearly. So that's equation 4 recalled, and then we plug in 5, 6, and 7. So lambda square a e power lambda t plus 2 zeta omega n x dot is lambda a e power lambda t plus omega n a e power lambda t equal to 0. E power lambda t is not 0 for any positive time unless it goes to minus infinity or something. So that's not 0. A is not 0 because if A were 0, it would be essentially a 0 solution and no motion solution, which is not what we want. So because A e power lambda t not equal to 0, as we want a x of t not identically equal to 0, essentially we have, well, a e power lambda t, which you can cancel, lambda square plus 2 zeta omega n lambda plus omega, this is omega n square equal to 0. Okay, so this equation, lambda square plus 2 zeta omega n lambda plus omega n square equal to 0 is called the characteristic equation, which again you might have seen, characteristic equation. You may have seen in your differential equations class. And we can solve this characteristic equation. It's just a quadratic equation in lambda, which implies minus plus minus square root of okay, so we just use this straight quadratic equation formula, and this is what we get. There is a 2 square here, which is 4. There's a 4 here. You can bring the 4 out, and then bring the 4 out of the square root becomes 2. So the 2 actually gets canceled throughout. If you want to cancel that. Okay, so we can rewrite this as minus zeta omega n plus minus square root of. Again, we have, we can simplify a little bit. There's a omega n square here, that's omega n square. And then there's a zeta square here, minus 1 divided by, well, that's it actually, because we just got rid of the 2. So let's simplify further. We get omega n minus zeta plus minus, well, let's actually maybe take it one step at a time. So we have minus zeta omega n plus minus, there's omega n square here, which if you bring out of the square root becomes omega n. So okay, so that's lambda. Okay, there are two roots, and so the solution x of t equals a1 e power lambda 1 t plus a2 e power lambda 2t, okay? Where lambda 1 and lambda 2 are the two solutions here, okay? So we're calling this equation 8, let's say. Let's call this equation 9. Equation 10, where lambda 1 and lambda 2 are the two solutions. It doesn't matter which one you call what. Okay, so that's the general solution, and then we can ask the question, hey, are these roots real or imaginary? And depending on whether they're real and imaginary, you can actually rewrite this general solution, or real or complex valued. You can write this general solution in different, more convenient forms. If, for instance, this was complex valued, you do not want to write it in this form. You want to write it in a different form, because if, yeah. Okay, so that we shall do in the next little video.